Have you ever looked up at a tree, a juicy apple hanging precariously from a branch, and wondered why it doesn't just stay there forever? Why does it eventually fall to the ground with a satisfying thump? This seemingly simple question has puzzled humans for centuries. It's a question that led a brilliant mind named Isaac Newton to formulate some of the most fundamental laws of physics, the very laws that govern our universe. But before we delve into the world of falling apples and brilliant minds, let's talk about something a little more relatable. Imagine you're trying to push a heavy box across the floor. The harder you push, the faster it moves, right? That push or pull you're exerting is a force. In our everyday lives, we experience forces all the time. A car accelerating down the road, a magnet attracting a paperclip, even the simple act of lifting a book, all involve forces. But how do we measure these forces? That's where our friend, the Newton, comes in. The Newton, named after Sir Isaac Newton, of course, is the unit of force in the International System of Units, also known as the metric system. It might sound like a fancy scientific term, but understanding newtons can actually help us grasp the world around us a little better. So, here's the big reveal: there is no simple numerical answer to what is a newton equal to. Unlike a meter, which is a fixed length, or a kilogram, which is a fixed mass, a newton is a derived unit. It's defined based on the interaction between mass and acceleration. Here's the technical breakdown. 1 newton is the force required to accelerate a mass of 1 kilogram, roughly the weight of a large bottle of water, by 1 meter per second squared. Let's unpack that a bit. Imagine that same heavy box from before. If you push it with just enough force to make it accelerate at a rate of 1 meter per second squared, which is a pretty significant push, that force you're exerting would be equal to 1 newton. Now, the force required to move an object depends on 2 things: its mass and the acceleration you want to achieve. If the box is heavier, more mass, you'll need to push harder, more force, to get it moving at the same speed. Conversely, if you want the box to zoom across the room in a flash, higher acceleration, you'll also need to exert a greater force. This might seem a little complicated, but it's actually quite elegant. The newton provides a universal unit for measuring force, regardless of the object or the situation. Whether you're talking about the gentle nudge of a feather or the powerful thrust of a rocket engine, newtons allow us to quantify and compare these forces. But the story doesn't end there. Newtons are the building blocks for understanding other important concepts in physics, like work and energy. Work is essentially the amount of force you exert over a distance, and it's measured in joules. Energy, on the other hand, is the ability to do work. You can think of it as a stored version of force. The relationship between force, work, and energy is a fascinating area of physics, and understanding newtons is the first step on that journey. So, the next time you see an apple falling from a tree, remember that it's not just gravity at play. It's the force of gravity, measured in newtons, that's pulling the apple down. And that force, in turn, is connected to the vast and fascinating world of physics, all thanks to the curiosity of one brilliant scientist and a well-timed falling apple. With that said, thanks for watching, and until next time.